Hi, today we'll be looking at a maximum likelihood estimate problem. So the question reads, in n independent coin flips, you observe k heads. Use the maximum likelihood principle to infer P of H, the probability of flipping heads. So before we even delve into n independent flips and k heads, we can kind of notice that we might be talking about a weighted coin here. That a coin that may not necessarily come up 50-50, but maybe it flips heads 90% of the times and tails 10%, or vice versa, or any combination of numbers in between. So let's try and build some intuition for this situation by taking a more concrete example. Let's say we flip the coin 6 times, and we wanted to guess the probability of flipping heads for this coin. If we saw heads 4 times and tails 2 times, what might be a decent guess for the probability of heads? So to my guess, it seems like a good estimate might be taking the total number of flips and dividing the total number of heads we saw by that. So we saw 4 heads and we had 6 total flips, so maybe the probability might be close to 2/3 for our coin. Of course, could it be a fair coin and we just happen to flip 4 heads? Sure. But given our information that we have from our flips, there's no reason to suggest that this probability should be lower or higher in any case. So now we have some sort of intuition that maybe 2/3 might be a decent guess for our situation. Let's see if we can try and build out a model for the general case and try to prove it to ourselves. So a good model for this situation actually ends up being the binomial model. And we can walk over that in a second. So since we're doing n flips and we observe k heads, we have n total flips. We're choosing k of them to be heads. So we use the choose function. And then we have heads show up with probability theta. We'll just define that. And then the remaining n minus k flips will be tails. So that'll show up with probability 1 minus theta. And that shows up n minus k times. I'll kind of gloss over why we use the binomial model here, but a quick bit about it could be, if we want to observe 1 head showing up, we have probability theta. 2 heads would be theta times theta, and then 3 heads would be theta times theta times theta, so on. So if we want to observe k heads, this would actually end up being theta to the k. For a similar argument for tails, we would also see that, for 1 head, 1 tails, it would be 1 minus theta. For another, it would be 1 minus theta again, so 1 minus theta squared, and then so on, right? So that would give us 1 minus theta to the inverse of, or the complement, so n minus k, total tails. Now, this actually isn't the full story here, because this kind of says, we want our first k flips to be heads, and then our last k flips to all be tails. In fact, we don't actually care that our first flips have to be all heads, but rather we just care that through our n flips, we do see k heads at some point. So that can be modeled with, the choose function. So we say, we have n flips, we choose k of them to be heads, and that'll give us all the arrangements. And then we multiply it by our k heads being chosen with probability theta, and then our n minus k tails being chosen, each with probability 1 minus theta. So that gives us a little intuition for the binomial model. So now how can we maximize this to figure out what value of theta maximizes this value? So the way we can do that is we can think back to Calc 1, and we can think about taking the derivative and setting it equal to 0 to find where our function is maximized or minimized. So let's give this a function name, L of theta, for the likelihood function as a function of theta. And now we can try and take the derivative of this. So on the right side, we get n choose k, that's just a constant, so we can bring it out. And then we have theta to the k times 1 minus theta to the n minus k. Now, if we think back to taking derivatives of two functions multiplied together, we know we're going to have to use the product rule. And to take the derivative of just this part and just this part, we can use the product rule. So doing that here, we have the derivative of theta to the k is k, I'll put this all in parentheses, k times theta to the k minus 1, and then we multiply that by 1 minus theta to the n minus k, and then add that to the derivative of 1 minus theta to the n minus k would be negative 1 times n minus k times 1 minus theta to the n minus k minus 1, and all of that times theta to the k. And we'll just wrap that with parentheses as well. So now from this, if we want to set this side equal to 0, we know that the choose function will never be equal to 0, so we can kind of ignore this or divide by n choose k from both sides. So the real interesting bit is going to be our big part in the parentheses right here. So that would give us 0 equals k times theta to the k minus 1 times 1 minus theta to the n minus k, and then plus negative 1, so I'll just do a minus here, minus, and in parentheses, n minus k times 1 minus theta to the n minus k minus 1 times theta to the k. So now we see that, we're getting somewhere, but there's still a good bit of kind of messy expressions. Let's see if we can try and factor something out. So we see that theta to the k minus 1 shows up, and theta to the k shows up here. And likewise, we see 1 minus theta to the n minus k minus 1 shows up, and then 1 minus theta to the n minus k shows up. So maybe we can factor these four parts out. So we have 0 equals theta to the k minus 1, and that's going to be multiplied by 1 minus theta to the n minus k minus 1. And then we can input what we factored it out of. So that would be k times 1 minus theta minus, and then n minus k times theta. So if we think back to the minimizing that we usually do in calculus, we notice that this gets minimized when theta is 0 or theta is 1, and then it probably gets maximized by this function here. Of course, we can always do checks to ensure that this is the case, but just for the sake of the tutorial today, I'll be concentrating on this part, since it's usual that the maximization happens sort of in the middle. But of course, it's always good to do checks. So we're really going to set k times 1 minus theta minus n minus k times theta equal to 0. When we solve, we get k minus k theta minus n theta plus k theta. We see that we have a minus k theta and a plus k theta. So we get 0 equals k minus n theta, or n theta equals k. So we find that theta is maximized when it is k over n. K over n. So seeing this, we can kind of see that, if we flip the coin and observe k heads over n total flips, we expect that the probability of flipping heads is going to be k flips, or k heads over n total flips. And we can see that actually does match what we expected from our situation above.